All right, guys. So this section, okay, is 4.6, solve exponential and logarithmic equations. Okay, so we're going to do a little bit of both. We're going to start with exponential equations, see what we can do with those, then go into logarithmic equations and figure out how to solve those. So again, 4.5 is a major section prior to this because some of those properties we will see again. So it's important that we understand those properties and we keep those in the back of our mind when we're actually working on these equations. All right, so we're going to do a bunch of examples today. As expected, equations is everyone's favorite thing to do. So, it shouldn't be too bad. But again, certain things we have to be aware of when we're working with them. Okay, so there's one major property that we have for exponential functions, and that's the property of equality. Oh, that might be a little too... Let's change the size of that. Okay, so property of equality. All right, and then this is going to be for exponentials. Okay, so the idea is if you have b to the x is equal to b to the y, if and only if x is equal to y. All right, so now, again, the if and only if statement here kind of just tells us that if we have this, then I can conclude this, and vice versa. If x is equal to y, then the exponentials should also be the same as long as the base is the same for both, okay? So now that's very helpful when we're working with some exponentials, especially with exponentials on both sides, because knowing Algebra 2, sometimes we need to manipulate bases so that they're the same, so we can go ahead and solve that particular equation, okay? So we're going to go through a bunch of examples where we are going to have to manipulate the bases to be the same, and you'll kind of see what we're talking about, okay? So let's look at our first example, okay? So we have... example 1. Okay, we have 9 to the 2x power is equal to 27 to the x minus 1. Okay, so now as you can see, okay, similar to the property of equality that's just listed right above, notice that the bases are not the same, so we cannot equate their exponents. Okay, so what we actually need to do is we need to find a base that both 9 and 27 do share. Now if you notice, they both are powers of 3. Okay, so we can kind of rewrite this as 3 to the second power to the 2x power equals 3 to the third power to the x minus 1 power. Okay, notice that we're forcing both of these to have the same base. Okay, so that's how we're kind of gonna approach this. All right, so now what are we supposed to do with those powers? We're supposed to multiply. So we get 3 to the 4x power is equal to 3. Now, when you multiply this 3 here, it's important that that gets distributed to both the x and the 1, okay? So you're going to get 3x minus 1, okay? Oh, sorry, minus 3. I just said that, and I failed to do that. Okay, so now, if you notice, the main thing that we're trying to get you guys to do here is to manipulate the base to be the same. Okay, so now that the bases are the same, okay, logically speaking, the exponents, if it's equal, should equal to each other. So now what we do is we set our exponents equal to each other. We have 4x equals 3x minus 3. Okay, and then what we're going to do is we're going to go ahead and solve for x. If I subtract 3x, I get x is equal to negative 3. Now that's going to be my solution for this first equation. Okay, so negative 3 was that exponent we're looking for. By manipulating the bases to be the same, we now have that solution. Okay, so again, we're going to do a bunch of these just to get used to what we actually have to do to solve for the exponent. Okay, so here's our second example of an exponential where we have to manipulate the base to be exactly the same. So we have 100 to the 7x plus 1 equals 1,000 to the 3x minus 2. Okay, so again, when we're thinking about this, we have to find the base, okay, and what base would make sense for us to use here. Okay, if you're saying 10, you're on the right track. We're going to convert both 100 and 1,000 to a base of 10. So 10 to the second power is going to be 100. So we're going to make sure that's a power of 2. And 10 to the third power is 1,000. So that's 3x minus 2. Okay, so now, like before, we're going to multiply our exponents. So we get 10 to the power of 14x plus 2 equals 10 to the power of 9x minus 6. And now that both bases are exactly the same, I am allowed to equate my exponents and solve that linear equation. Okay, so now we solve that. Okay, we subtract 9x, we get 5x plus 2 is equal to negative 6. We get 5x equals negative 8. Whoa, a lot of little mishap there. And then x is equal to negative 8 over 5. Okay, so there's your solution to the equation. Kind of straightforward once you kind of equate the bases to be the same. Right? Once the bases are the same, the algebra takes over itself, and it's not really too difficult of a problem, right? But, getting the bases to the same is what we're trying to focus on here, okay? Now, let's look at another example here that might take some time for us to actually identify what it is. Sorry. Let's do example number 3 here. Okay, so we have 81 to the 3 minus x power is equal to 1/3 to the power of 5x minus 6. Okay, so now 81 and 1/3. So now a lot of you, okay, we do not like to see fractions in our problems, but again, we don't discriminate, they're just numbers too, right? So again, let's identify what values might be best to convert both of these bases to, okay? Now, if you're thinking 3, you're doing very well because 3 is the one we want to use here. Okay, now while we're writing this 3 base, let's think of what powers is going to give us the expressions here that we have above, right? So we're trying to get 3, okay, we're trying to get 81 using a base of 3, and we're trying to get 1/3 using a base of 3. So 3 to the 4th power, okay, gives us 81. And then that's still raised to the 3 minus x power. And 3 to the negative 1 power is going to give us 1/3, and that's still 5x minus 1 as an exponent. Okay, so now, same as before, now we have our bases the way we want them, but we have to multiply these exponents. So we get 3 to the 12 minus 4x equals 3 to the negative 5x plus 6. Our bases are now the same. So 12 minus 4x equals negative 5x plus 6. This is going to be a quick equation for us to solve here. So we are going to add 5x. We're going to get 12 plus x equals 6. And subtract 12. We're going to x equals negative 6. All right, so there we go. There's our solution. X equals negative 6 for the third example. Okay, so again, in the beginning of the problem, our goal, again, was trying to get the same base. Once we got that same base, right, we're trying to get these bases to be the same. Once they are the same, we can go ahead and equate these two powers, and then it's just straightforward from there, okay? So that's one method of solving exponential equations, okay? But that's not always the case. You're not always going to have exponentials on both sides of the equations, okay? So let's look at some examples where you're only going to have an exponential on one particular side of the equation, okay? So we're down to example 4. Okay, so we have 2 to the x power equals 5, right? Now, when we did this earlier in the chapter, they gave us a lot of examples that we were kind of mentally able to get because they gave us all values that were easily attainable by some powers that we know from experience, right? But now there is no power that we can know mentally that's going to definitely work for this type of example. So what we have to do is we actually have to figure out, okay, how do I go about solving this, right? So remember from 2 sections ago in 4.4, we learned that inverses and logarithms are inverses. So we need to use the inverse property to help us get rid of the base of 2. Okay. Now, what logarithm is going to help us get rid of the base of 2 here? And if you're saying the log with the same base, you're on the right track, right? So log of 2, we're going to take the log of base 2 on each side. Okay. Now, what's going to happen on the left, since they're inverse properties, they're going to go ahead and cancel out. Okay. We're left with x equals the log of 5 with the base 2. Okay. Now, we recently learned how to change the base, right? So we can change this base really quickly. So we have, let's actually write log correctly here. Log to the fifth, log of 5 over log of 2. Okay, and then we're going to figure out what approximation that is, and that gives us. All right, so let's go ahead and see what our calculator is going to say. Actually, let me split screen this so we can have both. All right, so let's see exactly what we're going to get once Desmos decides to load up here. Okay, here we go. So we have the log of 5 divided by the log of 2. So we get 2.322. 2.322. All right, so there is your solution for this particular one. So if we took 2 and we raised it to this particular power, we'll get as closest to 5 as possible. Okay, so that is the exponent that we're going to want. That's our solution for x. Okay, all right, so let's continue. Let's do another example that's kind of similar to this one. All right, I'm going to keep the calculator open because we're probably going to need that for this next one. All right, so we have 7 to the 9x power is equal to 15. Okay, so same idea as before. Okay, we have a base of 7 that we have to consider about getting rid of because the x is an exponent. So in understanding the inverse properties of exponentials and logs, I know that the log I need to take here is going to be a log with a base of 7. Okay, so take the log base of 7 on both sides, and we know that when we take a log of the same base, that's going to simplify for us. We're just going to have now 9x is equal to this log here. Okay, so now we just have to figure out what that log is going to be equal to. So again, change of base property says we're going to go ahead and write this as log of 15 over log of 7. All right, so we're going to come here. I could quickly edit this here with Desmos. That's the beautiful thing about this calculator. All right, so we have log of 15 over log of 7. That gives us an approximation of 1.392, right? So 9x equals 1.392. Okay, now we want to take this approximation, actually, and we want to divide it by 9. So I'm not going to remove this number from my calculator. I'm just going to go ahead and click. Let's figure out what this is first. We get this value, and then we want to divide that answer by 9. So we have 1.392, and we're going to divide that by 9, and we get 0.155. Okay, 0.155. And then that's your answer. Okay, so that's how we obtain it. Similar problem. Again, this one though, we had to figure out what the logarithm was earlier before we decided to divide by the 9, and then once we were able to divide by 9, we got our final solution. Okay, but same idea, we're just trying to get rid of the base. In order to get rid of the base, we're going to use the inverse property of log to help us get rid of that base. Okay, all right, let's take a look at the next one. Whoa, where did all my work go here? Okay, here it is. And we're going to scroll up here. All right, so we are now on example 6. Okay, so we have 4e to the negative 0.3x. Just make that a 0.3 there, just to make sure you guys understand. Minus 7 equals 13. All right, so we want to solve this equation here. All right, so we start the process. First thing you're going to want to do, kind of just like you solve any equation, is we want to get the part that we want to isolate alone before we decide to do anything else. So here we have 4e to the negative 0.3x equals, we're going to add the 7, that's going to give me 20. Okay, now the base that I want to get by itself is e. Okay, so I can actually move the 4 here, and since it's multiplying e, I'm going to get 5, because 20 divided by 4 is 5. Okay, so now we're at the point where we have to get rid of the base e. Okay, so what's going to help us get rid of the base e? We have to use the appropriate log that's going to counter this e, right? So the appropriate log we're going to use here actually is going to be the natural log of e. Okay, and we're going to take the natural log on the other side as well. All right, so that's going to give me negative 0.3x is equal to the natural log of 5. So we come over here to our calculator and kind of figure out what the natural log of 5 is. All right, so let's see what we get. Clear all. There you go. Take it too long. Natural log of 5. 1.609. Okay, and then the last thing we're going to do here is we're going to divide both sides by this negative 0.3. So I'm going to take this answer and we're going to go back to 1.609. Divide that by negative 0.3. And we get negative 5.363. Okay, so if we have a decimal point right in here, if I can get to it, this is really not working right now. There you go. Okay, so negative 5.363 is my solution. So kind of if we just take a look at our work for what we did for this problem, we started by adding the 7 to the other side, got the 20, divided both sides by 4, we got 5. To get rid of the base of e, we need to use natural log. Natural log has the same base as e. So that's going to help us cancel out the e. And then we just have the exponent is equal to 1.609. We divide both sides by the negative 0.3, and we get our result. Okay. All right, so let's keep going. All right. Now, we kind of did a bunch of different things with exponentials, okay? So now we're going to kind of take a look at logarithmic equations really quickly. But before we do that, we need to talk about the property of equality for these logarithms. Okay, so property of equality. Okay, and now we're talking about logarithms. Okay, let me clean this up a little bit because we got a bunch of little marks here from my palm. Okay, so property of equality, okay, same idea. With logarithms, it's just now we're dealing with, same idea with exponentials, we're now dealing with logarithms. All right, so the idea is, let's say you have a log of x with a base b, and that's equal to a log of y with a base b. That's only going to tell us that x is equal to y, okay? Or vice versa, if we started with x equals y, then the log over here, the two logs are going to be equal, okay? So whether we take a log of each side or we just remove the log, the x and the y, as long as they have the same base, are going to be equal. That's one of the properties that they have, okay? So let's take a look at an example here where that's the case. So let's say I had the log of 2x plus 3 equals the log of x minus 1. Okay, so now look at the problem and identify here that they both have the same base. They both have a base of 10. So now, since they both have a base of 10, what I can do here is I can kind of equate these two here. All right, so let's go ahead and do that. So I get 2x plus 3 is equal to x minus 1. Okay, and then it's just a quick equation. So subtract x, we get x plus 3 equals, what do we have here? Negative 1. And x is equal to negative 4. Okay, now that's your solution. Now, the only thing with logarithms that we always kind of have to be careful with is if we ever get extraneous solutions. Now, if you remember extraneous solutions from the previous chapters, extraneous is a solution that occurs if when you substitute the value back into the equation, it fails as an equation, right? So really quickly, if we look at behavior of logarithms and how they work, we know that logarithm graphs tend to look like this, right? So one thing that's very important about logarithms is that the input value has to be greater than 0, okay? Not specifically x, but the input value. So let's actually write that here. The input for a log has to be greater than 0. Okay, so when I take my solution that we just found here and I plug it back in to both parts of the expressions here, are any of these parts going to be negative? Okay, and I'm sure you're answering, yeah. I think the easier one to plug it into is here, right? If you plug in negative 4, you're going to get negative 4 minus 1. Now that's a negative value for a log, and we just said here that you cannot input anything that's negative into a log. You can't even input 0. So this here is actually an extraneous solution. So because we only had one solution, then this is going to have a no solution case here. Okay. Algebraically, you did nothing wrong. Everything here was correctly done. But unfortunately, when you substitute that value back into the logarithm, it doesn't satisfy the function. Okay, and that's unfortunate because the logs they can't take any negative values when you plug them back in. Okay, so that's the reason why that one is an extraneous solution. Okay, so let's look at another one where we have to apply the property of equality. Okay, so let's say we had the natural log of 7x minus 4 is equal to the natural log of 2x plus 11. All right, so you have the natural log on both sides. Okay, you have a log on both sides. They're the exact same base, so I can take these two expressions and I can set them equal to each other. So we have 7x minus 4 is equal to 2x plus 11. So when we solve, we get 5x minus 4 equals 11. We get 5x equals 15. X is equal to 3. Now 3 is our solution. Again, we need to check to see if it's an extraneous solution or it's a valid solution, right? So if I quickly do some mental math and I plug it in up here, 7 times 3 is 21. 21 minus 4 is 17. That's a positive number. That's good. And then if I plug it up here, I get 2 times 3, which is 6. 6 plus 11 is 17. Also good, both another positive value. So 3 is actually a very valid solution, and that is the solution for our problem here. Okay, again, for these two types of problems, if you have a logarithm on both sides, you're just allowed to, a logarithm with the same base, let me clarify that, then you can go ahead and you can set the two expressions equal to each other, okay? All right, so those are very similar to those of the exponentials. These aren't too bad to work with, okay? But now let's start talking about some where you are provided with only one logarithm. Okay, so let's take a look at an example like that. So let's say I have a log, okay, with a base of 2 of x minus 6, okay, and that's going to be equal to 5, okay. Notice we only have one log, okay. So what we kind of need to do, just like we did with exponentials, is think about the inverse, okay. So if the logarithm here, okay, has a base of 2, what base is going to help me get rid of this log? It's going to undo this log. We have to focus on what base we're going to need for both sides, okay? And if you remember when we were working with inverses, the process that we want to do here is we want to exponentiate both sides of the equation, okay? So that base that we're looking for is going to be the 2, okay? So we're going to take both sides here, have a base of 2, okay, and the 5 is going to become an exponent, and so is this log. Okay. Now, on the left-hand side here, when you have 2 raised to the power of log base 2, we know since they're inverses, they have the same exact base. Voila, that's gone. Okay, so we have now x minus 6 equals 2 to the 5th power, which is equal to 32. Last thing we have to do is add 6 to both sides. So we get, not 8, 38. So x equals 38. Now, since we're working within a log equation, what must we always check? We have to check that this expression up here is still going to be positive when we plug into 38. When we plug into 38, do we still get a positive value? Well, it looks like 38 minus 6 is 32, so this is definitely valid. There's your solution, okay? So again, we just have to check for extraneous, any case that we're not going to necessarily have, you know, a negative value, because logs just can't take negative values. Okay, so let's look at another example. All right, so let's see what we have here ready for you guys. Okay, so let's say I take the log of 5x minus 1, okay, with a base of 4 is equal to 3, okay? So I got to get rid of this log, right? So again, you want to highlight the fact that there is a 4 here, a base of 4. So what base are we going to use to help us get rid of this log? That's right, base of 4, okay? So we're going to use the base of 4 on both sides to help us get rid of this log. Log base 4, we're going to cancel this. We're just left with 5x minus 1. Okay, 4x to the third. Okay, we know that that's 64. All right, so then we get 5x is equal to 65. And then we get a solution of x is equal to 13. All right, now, is it extraneous or is it a valid solution? Again, we want to plug that up here. Okay, so 5 times 13, we know is 65. 65 minus 1 is definitely 64. So this is not an extraneous solution. This is actually a valid solution. So 13 is our final answer. Okay, all right, so now, remember I said that the properties of what we were learning before will come into play again, right? So here's actually our first example where we're actually going to have to use those properties. So here we have a log of x plus 12 with a base of 4 plus a log of x with a base of 4 is equal to 3. All right, so let's figure out exactly how we're supposed to solve this. So we have multiple logs, but I see that there's an addition sign here between these two logs. If we follow the same rule set that we learned when we're supposed to condense these logs, what are we supposed to do with this expression and this expression? We're actually supposed to condense it using multiplication. So we're going to condense that. What is the product of x plus 12 and x? That's going to be x squared plus 12x is equal to 3. So you went from an equation, okay, that had multiple logs on one side, and you combined them into a single log like we did here, okay? So that's the goal. That's why those properties from before are very helpful. So now, what base can I use to help me get rid of these expressions? I could use the base of 4. Okay, what's going to happen with the base of 4 here is that you're going to cancel out that log. So now we can go ahead and continue. So I have x squared plus 12x equals 4 to the third power. 4 to the third power, that's going to give me 64. Okay, so now, okay, we haven't worked with these quite a while, right? But it's a quadratic. How are we supposed to solve quadratics? So we're going to set everything equal to 0. Let me move the 64 over. It's now going to be negative. All right, so now this has to factor. Okay, so what are two numbers that multiply to the negative 64 but add up to 12? So you're right, that's going to be 16 and negative 4. Okay, now what we're going to do is we're going to solve each of these. You're going to get x equals negative 16. x is equal to 4. All right, so those are the two solutions that you have for the problem. Okay, now what must we ensure since we're working with a logarithmic equation? We have to make sure that these answers that we have now, okay, these two here need to substitute here, okay, and they cannot provide a negative result. So if we start with the negative 16, what's negative 16 plus 12? That's negative 4. So negative 16 is actually what we call the extraneous solution. Okay. What is the 4 value here? Okay, so if I plug in 4 plus 12, that's positive. And then if I plug it into the second one up here, okay, it's just x, so it's positive. So this one's a valid solution. Okay, now 16 algebraically, or negative 16 algebraically, we got a correct solution. But unfortunately, that is not a valid solution for the equation. Okay, so we do get some extraneous solutions when we start to apply some of these properties. All right, okay, let's do another. All right, because those are the ones that are a little bit more tricky because you have to apply the properties from the previous section. All right, so let's say we have log of 5x plus a log of x minus 1 equals 2. All right, very, very similar. We have a sum, 2 logs. So that property we're going to have to combine using multiplication. So we're going to get 5x squared minus the 5x equals 2. Okay, now here we don't visibly see a base. Okay, so what's the base for the log? The base that we're going to use here is 10 because we know that if we don't see the base, it's the common log. That's the base we want to use. Okay, the log here cancels with the 10. All right, so we're going to have 5x squared minus 5x equals 10 to the second power, which is 100. Now again, as you can see, don't forget that the base of the log is 10 because getting the correct answer here, okay, is very, very important. 10 squared is 100, so if we get that part of it incorrect, we can throw our answer off in ways that we don't want to, okay? So just be very careful. Okay, so now it's just a matter of solving this quadratic. So 5x squared minus 5x minus 100 equals 0. We move the 100 over. Now this has a GCF of 5, so I'm going to factor out that 5. Okay, and then we need to factor this quadratic. Another simple case. So let's see what we get. We're going to get x minus 5, x plus 4. So x equals 5 and x equals negative 4 are the solutions that we got for our problem. Now we have to identify if any of these are going to be extraneous. So let's look back, okay, at our original problem. Is negative 4 or 5 going to produce a negative logarithm input value? Right, so again, we want to look here and we want to look here. All right, is 5 or negative 4 going to make any of these negative? Yep, that's right. Negative 4 is not going to work. So negative 4 is the extraneous solution. If I can spell it correctly, sorry for my mistakes. All right, so extraneous solution is negative 4. 5 is definitely valid though, right? 5 times 5 is 25, and 5 minus 1 is 4. Okay, so those definitely do work, okay? All right, so that's equations, okay? We covered many different types. We did exponentials that had the same base. We did exponentials that we had to convert to have the same base. We did the exponential on one side where we had to solve with a logarithm. We did a logarithm where both logs had the same base. So you can equate them using the property of equality. We had a logarithm on one side, and then we had multiple logarithms where we had to use the properties to combine them, okay? Don't forget, with logarithms, they're very restrictive, so you cannot have a negative input value. As for exponentials, that's never the case. Exponents can use whatever they want as exponents, so you can get any solution you want for them, right? So again, hopefully this video helps you guys. You know, it's very important on how to solve these equations because definitely, especially for your project that's going to be coming up. All right, so hopefully everything goes well. Again, just practice, see as many different cases as possible. Okay, and make sure you know how to you know what you're doing when it's come time to the homework. All right. If you have any questions, please leave a comment in Google Classroom or a message for me on Gmail. All right, guys. Thank you.